Thanks for the kind introduction. You see, my title, it's a bit long. Basically, we can summarize. I will talk to the fatigue lifetime computation of materials which are not so user-friendly. Yeah, so we have to adapt our methods a bit. And let me tell you what is the story behind of this, why I did this. So some of my co-authors, namely Nitzsche, Sebastian Henkel, and Horst Biermann, they are material engineers, yeah, and they like to do fancy tests, yeah, multi-axial loading, variable amplitude loading, non-proportional loading, and so on. And they really like to do this, and they do diffractive, but what they not like to do is to do any simulations, yeah, and this they will not do. And then comes the moment when my telephone rings and they call me, hey, Robert, can you give us a simulation? You're a mechanical engineer. We are not so motivated to do. And then we are going through the list, what they did. Yeah. Then we are talking, what kind of tests they performed. Is it total elastic or plastic, strain controlled? What are the amplitudes? What kind of measurement data are available? Most times it is the strain, so the elastic and the plastic strain, the stress, and the number of cycles until fatigue fracture. And what is then often my first step to do any further computations? I need to analyze the data to get any material data, namely the Baskin and Manson-Coffin parameters and the Rambert-Osgood parameters. This is often the point I will start, to analyze the test data. And just before the call ends, then my colleague said, by the way, we have some new experimental materials. We do not have a stabilized hysteresis curve, and we have some hardening effects, but you're a proper guy, you will handle this. Good luck. Yeah. And when I then look into the experimental data, I see something like this. Yeah. And this is not what you really like to see when you extract your material parameters. So what do we have on the left side? This is the stress amplitude over the number of cycles. And you see we have a strong hardening. We are starting just below 600 megapascal and end up higher than 1000. Yeah. And when we look on the hysteresis loops, here, these are all hysteresis of the tests. We cannot find any stabilized hysteresis. Each hysteresis is different from the other one. That is also not good. And here, this is one test out of the test series. But if we look on the whole test series, on the left side, this is the stress amplitudes. We see this hardening effect occurs for a lot of the tests, especially for the tests with a high total strain. Yeah. So here we have this hardening effect. And they told me the reason for this is that in the material, there's a change in the martensite content, which here I present the diagram taken out of this publication, but this is not really my field. I can live with the effect that it exists. It does not matter for me so much why it is. But what is interesting for me, how to handle these curves to get the material parameters. What I marked here with the star, this is the stress amplitude at half of the lifetime. Because normally when you analyze these material parameters, you analyze the hysteresis loop at half of the lifetime. This is the common approach. And if we look here, you see at half of the lifetime that the stress amplitude is still high and lots of cycles during the lifetime were done with lower stress amplitudes. Yeah, so far, but first step is to go ahead with this half of lifetime approach. Means you're taking the hysteresis loop at half of the lifetime, Then you're evaluating what is your elastic strain amplitude, plastic strain amplitude, and the stress amplitude. And with this and some regressions over all your experiments, you can determine your material parameters you need to do the lifetime calculations. Yeah, so this I did in the first step, and then you get here the results. The red is the numerical result. The blue dots are the experiments. I would say it's not that bad. Yeah, it's quite okay. But what I'd like to point out here, if we look a bit deeper into the results, is that in the numerical result, I used constant material parameters. That means my stress amplitude, it's constant during the test. Yeah. So here it's constant, and this is not really equal to that what we see in the experiment. There we have the hardening effect. So the question is it possible to improve the accuracy of the numerical result by considering this hardening, so the changing stress amplitude? Yeah, and this question I like to investigate or to answer here. And first, I have to show what is the impact of the stress amplitude in my lifetime calculation. So, yeah, short summarize how I do the lifetime calculation. So from the finite elements, I get a linear elastic result with a certain stress and strain. And then you do the Neuber correction, means you walk on the Neuber hyperbola until you meet your cyclic stress strain curve, here described by this Ramberg-Osgood equation with the parameters K and N. So here you get your maximum stress, and with this maximum stress, you can go in your damage model. Here I use the one of Smith, Watson, and Topper. So here we have the maximum stress, means this has an influence on the equation when we solve this to N. So you can solve the equation and calculate N. This is your lifetime. If your maximum stress is constant, you have to solve this equation one time, then you got your lifetime. But if sigma max changes, then here always you get different results. So the idea is to consider the maximum stress, maybe to do it each cycle, and then to interpret the lifetime or once by the lifetime as the delta in the damage. And you do this procedure so long until your damage value reaches 1. And therefore, you need any function, or you need to change the maximum stress so that this curve here changes. And this I solved by use functions for the parameters N and K. Yeah, to get this function, this is a bit, if you do it by hand, it costs you sometimes, because you have to analyze all your experimental data at not just at half of the lifetime. You have to do it more. I did it at 10 points. Yeah. And then you have it at 10 points of the lifetime. You have some here 10 points. And then I used a polynomial fit of third order to get these functions to describe the dependency of N and K, the dependency in the damage value of 1. When you use this, you get the following results. So on the left, this is the tests I already showed, but now we see the curve for the stress for the numerical result. Maybe you will see here that the stress at the very beginning, so this is the very first 1% of the lifetime, it's constant. There it turned out just for me that in the numerics, this is quite more stable, or without keeping here this constants, I got some non-feasible results. Yeah, here this area, it's quite big since we have a logarithmic scale, but it's just 1% of the lifetime. And then you see we have a change in the stress maximum. And what comes along with this is that we get a nonlinear damage curve. Yeah, this is why we use the change in the maximum stress. This gets nonlinear. And when we compare this now with the experiment, we are not exactly on the line, but I would say a bit better than keeping in constant. And I would also say we cannot be exactly equal since we have to do a regression or fit of n and k functions for all 7 experimental data. Yeah, not just for one. So, and now we have to quantify if the numerical result is better than the half of lifetime approach. This is shown here. Let me explain the graph. The blue line is the so-called best fit. That means if the numerical result is equal to the experimental result, you're exactly on the line. If you're away from the line, then you have some differences. So this here presented for 2 test series, and we see it's hard to quantify the result by 3 eyes. Yeah, so the dots are nearly the same. Means we need any number or any value to rate the 2 versions, and therefore I use the logarithmic standard deviation. This means, in other words, we just measure the distance between the point and the best fit line, and then we sum this up for all points, and then we get an overall sum as a measurement for the error, yeah, to quantify this. So, and when we do this, here the results are in a big table, but we can highlight 2 issues that especially for high total strains here, we can see that the numerical results, when we use a function for n and k, I would say are quite more close to the experimental results than the half of lifetime approach. My interpretation is that especially for this high total strain, we see more this hardening effect than for this low total strains. Then I would say especially for these results, we are much closer. And what is interesting to quantify is here, if we look into the sum of the logarithmic standard deviation, so our measurement to quantify. And there we can see that the numerical results for function n and k, there the error is quite lower than this half of lifetime approach. Yeah, also for the second test series. Yeah, and I agree to you, the difference is not that big. Yeah, my motivation was to do a big step forward. Maybe I did half a step. Yeah, but important is we are going in the correct direction. So it's not a step backward, it gets lower. And one disadvantage of the method is that we have to do the lifetime calculation each cycle. Yeah, normally constant parameters, you have to solve the equation 1 time, you have the lifetime, that's it. Now we have to do it each cycle. So this costs us more computational time. And therefore, I'd like to show my last approach that to reduce this issue is the approach just to keep the parameters constant, maybe just for 10 cycles, 50 cycles or something. And the impact here for this example, it's not that big, yeah, in the computed lifetime, but you can reduce massively your computational time here to 5% by using maybe an approach with 20 cycles, keeping the parameters constant. So it is an issue, but you can reduce it. Yep. So, and finally, I'd like to conclude, considering this variable stress amplitude improves the accuracy Yeah, what is open? We do not just have to adapt the Rambeck-Osgood curve. I would say we have also to consider the Baskin and Manson Cosmos parameters. They do also change, yeah, since our hysteresis loop changes all the time. So there I'm working on. I have an approach, but I think it's not ready for publication, yeah. And also the method presented here, I should test with more experimental data. And what is now prepared? The calculation, so the damage per cycle. Maybe it's the basis really to do also variable load amplitude tests or computation. Since then, we can take sequence effects into account when we jump through the total strain levels. Thank you.